Yes. So can we begin?
Yes.
A very good morning. It's always a pleasure and a privilege again to be at the IGNO course on sustainability science. Today, actually, we are moving towards another very important topic in sustainability science, which deals with water. So this is actually block 2 land and water resources. And today we will be discussing water from the perspective of its status, distribution, and quality, as well as competitive uses. So yesterday, actually, we started in the previous class rather, that we thought about ecosystem in different ways. And now the extension of this idea on addressing what are the issues related to its status, distribution, and quality brings us to the sphere of water today. So today, actually, we will be looking at the aquatic ecosystem in detail. I want to take you all back to the slide that we discussed in detail yesterday, and let you appreciate how actually different processes versus the different components of an aquatic ecosystem, as we have shown here, have multiple functions. So it is not just one function. For example, site runoff, if we say, is a part and parcel of the land environment, which is in close association with the aquatic environment. But this process itself, part of the component which is called the land, it actually has manifold impacts on the aquatic ecosystem. Similarly, if you see, the outflow from a system such as a lake will have definite impact on the surrounding soil. So here we are seeing that there are multiple functions to the aquatic ecosystem, as we have understood.
Dr. Harini, your network is, there's some problem in network.
So can you hear me now?
Yes.
And are you able to see the screen?
Yes.
Okay, I'm very sorry. There was a temporary network lapse here, and I think I went out of the network for a few seconds. But what I was telling is that the multiple functions of aquatic ecosystem, which determine its functionality on the whole, is divided into two major categories. The first functionality is to make water the medium which is available for all life to exist and grow. And also the second component or functionality of these ecosystem as such is to distribute the water towards all landforms where it is not available, so that other functionalities of the land, such as agriculture or the growth and development of other organisms, those are also facilitated. So here there is a distinct relationship between not just the surrounding of an aquatic ecosystem, but on a larger scale as well. So this is the idea that we have to imbibe when we are thinking about the association between the biotic and the abiotic components, which we have been seeing in our slide till now. So now to actually go to the exact ecosystem services we were talking about, aquatic ecosystems, first of all, are actually the services that they offer are in different dimensions. The first dimension is as an ecological unit, as we have seen, of the structure of providing the habitat, niches, and the refuges. The second most important dimension is the environmental link that it has. for the functional pathways of biogeochemistry and the exchange of nutrients. The third and the most important dimension and very crucial one that aquatic ecosystem contributes to as a service is as a source for energy. Okay, so for aquatic as well as terrestrial flora, that is why I said the reach of the aquatic ecosystem is not confined to its own spatial boundaries, but it goes beyond its spatial boundaries. So in that sense, it is a source of energy not only for aquatic organisms, but also for terrestrial organisms. And we are going to discuss this point in detail. I'd like to you to concentrate on this specific point. We all know that as a biological unit, aquatic ecosystems contribute to the global biodiversity in manifold ways. Okay, so they are actually, water is known as the elixir of life, and actually oceans cradle of life. So we know that water in any form will contribute to biodiversity and its richness throughout the world. Also, finally, if we can look at this ecosystem in entirety, it is a system of entities that can provide feedback controls on the global processes as well. So actually, if we see, water ecosystem or aquatic ecosystem is such actually a malleable and a very adaptive environment, which actually manages these controls towards the feedbacks for both the natural processes as well as the anthropogenic processes. And these alterations are very, very important for determining the global overall ecosystem stability. So let us see how. Now, this slide actually tells us that it is very important for us to understand the interlinkages. Now, if we count the, from an ecosystem perspective, if we count the number of ecosystems here, we find 4 different ecosystems. One is a river, a lake, and a sea. And the 4th one is land. So there is an integration of all these ecosystems that we are seeing together, which actually contribute to the status or the trophic status for this particular, not just one ecosystem, all of these ecosystems, as well as this particular region, bioregion as well. So if we look at it, we have to understand these processes and impacts, we have to study the status of these ecosystems first. Studying the status has 4 different major steps. One is, first we have to identify the trophic states. We have been discussing about these trophic states in detail in one of these classes when we discuss the concept of ecosystems, and we understand that the trophic levels change and the populations and the abundances and their interactions with subsequent trophic levels also change within an ecosystem. So when we have to identify what is the status, we have to first identify what is the the trophic levels which are in existence and what are the food webs which are in operation. So identify trophic status is the first step. Next, we have to understand what are the exchanges that these ecosystems have with adjacent ecosystems. So we can say that now if we take only the aquatic ecosystems part in this particular slide, we can identify there is going to be an exchange between the river, the lake, and the sea. So this is what we call as a continuum. Now, apart from this continuum, there is also a distinct continuum of each of these ecosystems with the land ecosystem. For example, we can classify that as a river land continuum, lake land continuum, and a sea land continuum. So these processes are not restricted only to these particular ecosystems or isolated. We also have to quantify what is the nature and how much of exchanges are taking place with the adjacent systems. So this helps us to judge what is the status for each of the aquatic ecosystems that we are studying. Third is to integrate multi-modal data. So it is not just enough if we know what is the the trophic level or the ambient status. We have to know how this is changing. So for that purpose, we also have to understand the quality changes that the ecosystems have to undergo. For this, I do this using many indicators or proxies. So these indicators tell us that how much or how less the ecosystems have changed in their quality over a period of time. Finally, with these 3 major inputs, we can derive the insights, which are very, very essential for us to understand what is the state and function of these aquatic ecosystems. We are going to, discuss these points in detail in the coming slides. Now, I'm going to take you to identifying what are the forcing factors and proximate causes which determine what is the status for an aquatic ecosystem. In this slide, you see there is a definition for two important terms that we have to understand. The first important term is forcing factor. Forcing factors are the factors that cause a change in the ecosystem characteristics under normal as well as altered conditions. So we had a very good discussion on how the stable states themselves can change in time, right? So aquatic ecosystems are very, very dynamic ecosystems where the stable states can change or alter. If they are not disturbed in a period of time, they can attain what are known as altered or alternate stable states. So even under ambient or altered states, what are the changes that the factors which cause these changes under ambient as well as altered states? This is our forcing factor. Examples of forcing factors are precipitation, temperature, wind, nutrients, which are always present. Okay, they are ubiquitous. Second a term that we see here is something called as proximate causes. Proximate causes we have to actually distinguish from forcing factors, because proximate causes are those which bring about considerable alteration from the ambient status. So this actually helps us to determine when there is a steady state, how the deviation is actually occurring. For example, activities such as mining, agriculture, industry, land use changes, water course alterations, damming, for example, is one good example. Groundwater extraction, deforestation, urbanization, all these are proximate causes. But the ultimate forcing factors is another concept that we are moving from. The basic or the ambient forcing factors that leads to destruction. Okay, so what is the impact? In earlier slide, we saw the terms processes versus impacts. Now, to judge how the status has changed, we have to understand that ecosystem destruction, habitat alterations, water chemistry alterations in aquatic ecosystems, as well as the changes in the species abundances and richnesses. All these are the ultimate impacts, which we call as ultimate forcing factors or ultimate impacts. So in this slide, we can see that ecosystem changes, we understand it can be caused due to constant or periodic changes in the stable states. This is another consideration we have to understand. So the term that the processes alter the stable state of an aquatic ecosystem can be short or a long term. So here, and it also can be constant or it can be periodic. So the ultimate impacts are in the form of ecosystem destruction, changes in abundance, changes in communities, but very specifically to the aquatic ecosystem, there is a change in the hydrological regimes. So actually, there are sub-factors which cause these changes in the regimes and the habitats themselves. Those sub-factors can be it can be periodic or it can be, chronic over a long period of time, but they are very, very, very intense. For example, acidification, acid rain, okay, changes to riparian corridor or the area around a lake shore, if you see, or a river shore, on the river banks, what are the changes in the vegetation? Then eutrophication. Eutrophication is a new term that we look at, where it indicates excess of nutrients in the water, okay, aquatic ecosystems. We will be discussing about this. Also, another term called siltation, which means more of silt is getting suspended in the water. So these are all actually normal or anthropogenically induced factors, which we call as sub-factors, which change the states or the status of aquatic ecosystem. So they help us to determine how to achieve whether a given system has achieved an alternate stable state, or is it still in a disturbed state, or is it in an ambient state. Good example from an urban point of view. We are also discussing about the urban ecosystems. The urban aquatic ecosystem point of view, change in the state of a lake from being a natural lake to a dried lake bed back again to a sewage fed lake. This is actually a tried and known model in some cities in our country, where the sewage treated water is let into the lakes to revive it because of the presence of nutrients and the presence of characteristics which are ambient for other microorganisms to exist. Slowly it gets repopulated with other communities of organisms across different species. So this is one example of how from a stable to a disturbed or back to an alternate stable state, which is not actually equivalent to the natural stable state. These sub-factors can determine how the impacts or the ultimate forcing impacts have had on the ecosystem status. This table from Malmquist is a very important compilation, because this tells us in detail correlating between the forcing factor, the sub-factors, the causes, with actually the abiotic and the biotic alterations, right? So the abiotic changes that we see here will directly lead to biotic implications. So now we extend our understanding gradually from understanding the forcing factors, sub-factor, along with their proximate causes, to understand how abiotic alteration is caused because of these changes. So for example, let us look at the example given here on habitat alteration, damming, channelization, water abstraction, deforestation, or transfer schemes. These are located as proximate causes which actually lead to loss of natural flow periodicity. So this is a very important consideration, because when we actually look at the proximate causes, we can connect it to how abiotic system itself is actually affected within the aquatic ecosystem. There actually, normally there is a flow periodicity, but increase in the flow or decrease in the flow can cause the loss of this natural flow periodicity, leading to an increased risk of drought and severe upstream downstream issues, as well as the reduced substratum complexity, which can actually help in nutrient recirculation over a period of time. So the biological implication of this will result in reduced biodiversity because of altered habitats, also reduced dispersal because of the fragmented habitat conditions. So here actually we see that habitat alteration as a consequence of any anthropogenic activity on an aquatic ecosystem can have these state change very significant and cause this over a long period of time also. So like that, we have other forcing factors and sub factors. We may not be able to discuss all this in detail, but this is available for your inquiry a little later. Let us now take something that we are looking at from the flow periodicity angle that we just discussed. So now when we are actually talking about the status, we also have to have some parameters to quantify this, as we said, right? So the four steps that we saw earlier, according to that step, we are quantifying the status now. So how do we quantify? Is through actually identifying the processes themselves. The first very important process in a flow, in characterizing the flow of aquatic ecosystem, is what is known as surface runoff, which is just, precipitation or rainwater flowing over the ground. Now this runoff enters major reservoirs. What are the reservoirs? The possibilities are rivers or streams, and lakes, coastal lagoons, and finally the oceans. So now we understand that surface runoff contributes to what is known as a stream flow. Okay, a stream flow now is the volume of water per unit of time in a river or stream. So now we are bringing in the temporal component to help us understand how much of water is added within a particular period. So now the unit of time helps us to judge that the flow has been, how much has the flow been. And also associated with this understanding of the processes is the process itself, which is known as infiltration, or soaking or entry of water into the ground. So now, whenever there is a hydrological cycle in place, we have a runoff through precipitation. precipitation hits the land, it joins streams and becomes a stream flow, and it actually reaches the ocean on the surface. Apart from that, there is also infiltration through which water enters the groundwater. Very specifically, we have these terminologies here. I would actually bring to you your attention to what is known as the interflow or quick return flow, which is the second row. Okay, here the interflow is that water which flows through the upper soil layers but does not become groundwater. Okay, so this is very important for us to understand that this contributes to what is known as water logging on the surface, and it can appear in runoff in some point of time, but it does not soak through. So this interflow is very important to preserve the moisture content of soils. Okay, so this is a very, very critical factor, which is not which has to be quantified if we have to actually determine the status of any aquatic ecosystem with reference to what is the volume of water it is receiving and how much it is actually retaining within its system. Similarly, if we look at a term called base flow is that water which flows into the stream from natural storage, that is the aquifers. Aquifers are reservoirs of water underground, and they are actually contributing to this base flow actually is contributed from ground flow and not the surface flow. So this sort of differentiation for us between what is actually water that comes, where it comes from, and where it goes, it gives us an idea of what is the status of an ecosystem when we study its different processes and structure and components. Now, another very important terminology here, interception, refers to a part of the precipitation at the beginning of a storm event, which does not go into base flow or the surface flow, but is stored in the vegetative cover in the canopy or retained as in the vegetal covers. Okay, so this does not contribute to runoff at all. So these are essentially the water that the trees or the vegetations capture. So this is another very important consideration. Why we are talking about all this? Because we look at the aquatic ecosystem from a mass balance approach as well. We want to see how much of water is conserved. Also, from the flux point of view, we want to know what is the water flux. So for identifying the status, we need flux estimates and we need base flow. We need flux estimates and the mass balance estimates. Only then we can actually quantify how much of water is stored and how much is actually returned back. So here, another very important term that we should know is aquifer. Aquifer itself is an underground layer of water-bearing rocks or permeable, it should be permeable soil materials, which restores the fresh water over long periods of time. So groundwater extraction, a proximal cause, can cause definite alteration in the aquifer characteristics. This is something very important for us when we are, if we are given the task of judging what is the status of a given aquatic ecosystem, is it being sustainably used? The first thing that we should know is a component that we should address. What is the component that we should consider? The first component is groundwater component, and the first reservoir that we should consider is the aquifer. So now percolation, which is the infiltrated water seeping down into the aquifers, is part of the process which helps to sustain these aquifers. So that is also a very important input for us. So in that way, if we see infiltration versus percolation is a very important characteristics which contribute to the soil profile in terms of pore water as well as on the superficial layers as soil moisture. Now if we see, there should be a balance between surface availability and infiltration when we are judging how much of recharge of these aquifers is happening over time and what reservoirs are contributing to this recharge. So moving on. Now we see concept of a watershed. Okay, we have actually seen the integratedness that aquatic ecosystems have with the land. This is exactly the way that it contributes to our understanding of the status, is to see this as a watershed. It is a bounded area of land where water naturally drains towards the lowest lying point. So this is very important, and this boundary will direct where the water will flow and which direction it will flow. It is always from the high to the lowest point, which is called the watershed outlet. And the flow is hindered by the presence of depressions or basins which collect these water over period of time. So this can also be called what is known as a drainage area, sub area, basement, or a catchment area. So this constitutes our another component of assessment of the status of a water ecosystem. Now, going back to the cycle, we'll be able to appreciate this better, because now we know that we have to identify the functional components which contribute to the water mass balance and flux as a whole, and contribute to the aquatic ecosystem properties and services. We also have to know that we have, for a sustainability point of view, we have to conserve these water and ecosystem services together. Now we are moving our attention from the status concepts to what is known as distribution. So from the distribution point of view, we see that water is distributed majorly in the oceans, right? So now, apart from the 97.5% which is present in the ocean, the 2.5% is what is contributed as the fresh water, right? So among this 2.5%, we have the ice and glaciers, the groundwater, the lakes, marshes, streams, and the atmospheric and biological water. See this, I'm putting the ice and glaciers separately as 68.9. Please don't get confused by that. That is part of the 2.5% of fresh water, which is stored as ice and glaciers, but the state in which it is present is different. So it has to be classified separately. Now, if we see ice, is a solid state of matter, solid phase of water, and it is present in the solid phase locked up as ice. But actually the impact of humans can actually lead to excess of this being contributed to the overall 2.5% that is available on the globe. So now, but within this 2.5%, if you see, 30.1% is present as groundwater, only 30% probably. Okay, so this 30% that we have is surely available in the liquid form for us to extract, but the use of this needs very, very precautious attempts to actually extract, use, and reuse. Okay, so this 30% is a very critical component which needs our attention from usage point of view. But if we see lakes, marshes, river streams, which contribute to about 0.6 to 0.7%, if you see, it's only that much which is stored in natural ecosystems. And from this, the criticality point of view, we can appreciate how it takes so much effort if we pollute or degrade this 0.7% water which is present in these ecosystems. It takes so much effort and so much money and so much, I would say, vision to actually restore back if we degrade this amount of water. But these are all actually ecosystems which sustain life at different scales. And without them being present, there is no way that we have this 30% of groundwater to our use, and we will not have the ice and glaciers, 69% of ice and glaciers, which are locked up for our use or for natural recycling on the earth. So now the more we see, the lesser the amount of water that is partitioned, the more critical it becomes. In that way, if you see, 0.04 can be a very small unit that we are talking about, 0.04%. But this is the amount of water that is present in the atmosphere as well as in the biological realm, as within our cells, plant cells, and all the cells that are present, how the water is locked up biologically. But this 0.04% makes a big difference to life itself. So that is why I said the more lesser water is in its quantity, the more critical it becomes. So we have to appreciate this distinction or distribution in a way that helps us to appreciate how much of sustainability is perspective is required to actually manage these critical elements as well. I want to take you to another way to understand this. One way we talked about runoff, right? So what is the global runoff? The global runoff is about 40,700 kilometer cube, accounting for net precipitation on land, which turns into floods. So you see, that's a huge number. And 1/5 of this actually occurs in remote geographical locations where these locations are not used for economic purposes or not viable. Especially examples are desert and especially arid regions where this is not very economically viable ecosystems which the aquatic ecosystems share or are on continuum with. So now if we see, the 31% of this runoff is the amount that is accessed by humans as well, which turns out to be around 12,000, approximately 12,000 kilometer cube. And this 12,000 kilometer cube is what is known as accessible water. And this increases if we increase the number of dams or flood storage capacity or rainwater harvesting measures. Okay, so we are trying to increase this percentage. However, we should understand Postal et al. 1996 paper is one of the classical papers which discuss these issues in very great detail, and they have estimated that the accessible runoff cannot increase beyond 10% in the next 30 years. Okay, so this is based on the observations of runoff, flood, and storages across the globe for a 100-year period that they have done. And they have said that in the next 30 years, how many ever dams we build, how many ever assets we create, we cannot increase this accessible runoff to beyond 10%, which means that this climb can be something critical when there is a huge population explosion. And humans at present are exploiting about 70% of the available accessible runoff, which means that in the same period, if there is excessive population growth, the achieving more increase of accessible water is always going to be a challenge. So this is where the distribution issue is magnified. What we said as a critical issue as we go down and availability lessens, but the criticality increases, becomes even more critical now because of the narrative of population growth that we are looking at. And this actually leads to what is known as water stress. So now we have some definitions that we have to understand in relation to distribution aspects of water. The first aspect is water stress. Water availability in any region is reflected by what is known as its water stress index. Okay, so this is actually a minimum per capita water requirement that is available for an individual in any part of the world. So the area is supposed to be water stressed if the annual per capita availability is below 1,700 cubic meters. This 1,700 cubic meter estimate is continually revised based on the estimates of water reserves that the world has. Okay, so we have to understand, but for an idea, 1,700 cubic meters per person per annual per capita availability of water in a given area can account for what is known as a water stressed condition. Okay, but if it is below 1,000 cubic meter, it means that region is a water scarce region, or there is water scarcity scenario prevalent there. An absolute scarcity scenario is when the water goes below 500 cubic meters. So this is actually something that we have to understand in terms of quantifying the status versus the distribution. Now, the status is one aspect, distribution is another aspect, because we can use what is available to us in a particular region, or we can divert it from somewhere and still use it. So water as a commodity has these two particular dimensions with which we can say if a region, it need not be that a region which receives very scarce rainfall should be a water stressed region or a water scarce region. That is an understanding that we develop from sustainability point of view, given the engineering solutions and the diversions that are available naturally in the form of rivers, or even water logging cycles which are present. It need not be that these areas are going to be water scarce even if precipitation is less. But characterizing what is the availability gives us an idea of actual water scarcity, water stress, or absolute scarcity. Now, through living standards, if we see, a renewable water supply of 2000 cubic meters per person per year is adequate to support life. Okay, so the key term here is renewable. That means every year we need to renew the water supply by 2000 cubic meters per person, which will result in healthy or adequate living standards. If the water availability is between 1000 and 2000 per capita, cubic meters per capita per annum, then the region is said to be water stressed. If the availability is less than 500 cubic meter per person per year, this region again can be called as water scarce. And now it's under normal conditions, it has been estimated that the global water renewable supply is about 7,000 cubic meter per person per year, which means that there is actually adequate water which is actually available for having healthy and very good health, sanitary health conditions, right? So here actually the sanitation, hygiene, also availability for basic requirements like cooking, these are also very, very important considerations when we look at the global renewable supply point of view. From that idea, if we look at the world at two different time periods, as is shown here, you see there is one time period, a snapshot of 1995, another time period 2025 in terms of the water withdrawal. So now we know from our idea on the status and distribution, we know that drawal of water is in different ways, one from the surface water or from the groundwater, and also distributed through other anthropogenically made systems like canals, for example. Also, we have to understand that there is some water which we will never be able to use, that is stored in the vegetation or the ice or glaciers. We are leaving that. Apart from the other aspects, the 2.5% of fresh water that we were considering, based on that, the withdrawal of this 2.5, we estimate that 2/3 of the world's population can be under severe stress conditions, water stressed conditions by 2025. So that is what is shown in this map, which is drawn by the Meteorological Organization. It is an old map, but it is still relevant today because it shows very typically, if you compare across these maps as well, that there is a huge mismatch between the regions where the population is high and where the fresh water is available on a global scale. So here, people, the high populated areas have low water resources to compensate or give adequate living condition for its citizens. So the mismatch is of a distribution problem by nature, and 3 billion people are likely to be affected by water scarcity by 2025 is another estimate, which gives us the idea that the number of people suffering from water stress and water scarcity is bound to increase by 2050 as well. So according to this projection, if we actually consider how or the ways in which we can actually look at water use itself, we actually come to 4 different sectors where the global water is used. One is the agricultural, the domestic, industrial, and reservoir storage. Okay, so these are the 4 different components where the global water is used by the sector, the major 4 sectors. So agricultural sectors among these 4, if you see, they have the highest withdrawal rates and they have the highest consumption rates. It's actually significantly higher compared to domestic, industrial, or reservoirs. So from a normal point of view, we will not expect, we do not pay attention to amount of water that goes into agriculture, because we are all trained to look at the industrial aspects as major sector as the major user of water, okay, apart from the domestic sector. So we actually, because we all also waste water, we try to not give attention to the domestic water usage sectors most of the times, because we just get and use water. We are also, even though we suffer from water scarcity sometimes in a year, we really don't pay heed to what we are going through from the domestic sector point of view. But the realization that the industrial sector, among the three major sectors of agriculture, domestic and industry, they are the lowest users of global water, is something that it's very strange for us to accept. But this is actually where the data tells us that it is the withdrawal and consumption versus waste generation is typically lesser for the industrial sector. But with the increase, there is one factor which can topple this sort of idea that we have across the sectors, and that factor is population. With increase in population, where developmental needs actually saturate to a high extent, then the water actually is diverted from agricultural domestic use more towards the industrial use. So this is actually where sustainable use of resources concept becomes very, very critical. Where are we using our water? Are we using it to grow our food, or are we using it to grow our industries? And there has to be a balance. Okay, so the snapshot that we are seeing here is especially for the developed versus developing countries. And here you can see that for the developing countries, it is 6 times greater from the for the developed countries. The water consumption Am I audible? Can you see my screen?
Yes, madam.
Yeah.
Okay. So again, sorry for the the slight interruption in this presentation. I'm just going back to the slideshow format again. Can you see the slide?
It's visible, ma'am.
So on slideshow, is it visible now?
Yes, ma'am.
Okay, thank you. So I was talking about how the developed versus developing countries, how the narrative, progresses across different sectors, agricultural, domestic, and industrial sectors. So we can see that it is the domestic water consumption in developed countries is 6 times higher than in the developing countries, which we actually don't, we cannot expect or predict that. But what is very interesting is these developing countries, where the population climb is going to be higher, will catch up with this use pretty soon. So here the reservoir aspect, the sector on reservoir becomes very, very critical. But there is one deterrent which actually determines how less the water assets that we are creating are able to store water for us, and that is the increase in evaporation. So the global evaporation rates are also increasing over the years because of excessive overland heating and excessive heat stress that the globe is undergoing. So that aspect actually has a negative feedback on how much of water can be sequestered in the reservoirs. So here actually we see that the problem of distribution is deviated across or permeated across different sectors at different levels. So it is not going to be the same at all periods in time for all countries. Hence the sustainable use of this resource becomes very, very relevant. Now, if we see, especially for India, where India is an agricultural country, the need to feed more than 1 billion people and the expanding population. Recently, we heard the news that we may overtake China in the population statistics itself, is very, very essential because we have to balance this with our expanding industrial growth also. So here that the percentage of fresh water used is more close to 100, right? If you see 100% use. So 79 to 100% is classified. India is classified under this category, which means that there is huge stress on our water resources. This slide actually is one of the latest from the Sustainable Development Goals report that was released in 2022. It shows India under region of between the regions of scarce and stressed, right? So here you can see that the stress or scarcity is very, very high. And there are several parts in the world which also, exhibit this kind of a scenario. But the vulnerability is also, higher where the regions of stress and scarcity are located. We have to understand that there is a set of indicators which tells us how well India is performing on the goals of sustainability itself, which we have discussed earlier about the Sustainable Development Goals. Now we can see in terms of SDG 6, India's population, which is using at least the basic, which have access to basic drinking water services, is about 91%, which is very good, right? So India also has basic sanitation services to cater to about 71% of its population, which is again a good estimate compared to other regions. You can see that the green arrow, which says the population having at least basic sanitation services, has climbed, which is a good trend. But if we see that the anthropogenic wastewater, which receives treatment and adds to the water pool itself, it is only 2.2%, which is very, very less. So in that sector, that requires more work, right? And also the scarce water consumption embodied in the import sector, that also actually is very, very huge, which means that 97.4% is the scarce water consumption through imports. Water is required to produce or manufacture different products, and in that process we consume water. So this exact parameter indicates that there is huge consumption of water in that sector, which has to come down. So here actually we see that India is performing relatively well, but it is still under scarce water or scarce to stressed water conditions, which makes it very, very vulnerable. So now we understand the 3 dimensions that sustainability of water will depend on its availability and how it is used. So distribution and use becomes very, very important. So this, I am going to take your attention towards the use perspective today. Now, use is where we said earlier that there is going to be a status change or an alteration in the stable states, which can cause a change in the water quality. So here the water quality changes from letting untreated industrial wastes or runoff from agricultural fields, untreated municipal sewage, all this cause a change in the quality of water, and makes the quantity that is available to us even lesser. So from that aspect, if we see, it becomes that we have to understand this from the perspective of water quality itself. So water quality can be studied in different ways. One is the physical, another the chemical, and the third biological. So these are major ways in which we can characterize what is the quality of water that is available to us. We are going to look at some of these parameters today, just to have an understanding of how these parameters relate to how much, what are the manifold ways in which the water can be used, and how much of this water can be used overall, right? So if we say the first parameter, see here, the temperature. Temperature, as we know, is water temperature, which is how it is measured is using what is known as a digital thermometer. It is actually measured in situ. In situ means where it is found. So to characterize an aquatic ecosystem, we need to measure its temperature first. Then there can be samples which they are taken back to test the odor and the taste. So the odor testing should be done 5 minutes of sample collection, within the 5 minutes of sample collection, which means that it is a very dynamic parameter, and it can be done automatically in the field itself. And taste is often done mostly only at the treatment plants, water purification plants rather. It is not good for us to just take some water and taste it, but it is actually a very good indicator of the quality as well. For groundwater, it is a good way to judge the water quality, because most people, what they do, they'll take the groundwater and taste if it is a sweet water or a salt water. It gives an idea of what is the quality. So the sweetness and saltness actually correspond from the physical domain to the chemical domain. Okay, the presence of salts, these tell us how sweet or salty or otherwise the water is. Now, this another aspect that we have to see is what is known as total suspended solid, and with that, what is known as the turbidity of water. So the quality of water defined by TSS tells us that how much of residue is present when the filtered water is filtered and the filter is weighed and compared to the original sample. So when the number of suspended solids is higher, the concentration of total suspended solids will also be higher, which means that the water that is filtered is actually having more of these solids, which may or may not indicate directly upon the exact quality of water, because in some extent, in some instances, it can be just dried leaves or debris which contribute to these solids. So there has to be a closer look at it from the turbidity perspective, which means that how much of this solid is being suspended. That is actually measured by the amount of light that is scattered by the sample. Here you can see we have a few demonstrable flasks here, where the turbidity is higher in the one that is on the extreme left hand side, and the one on the extreme right hand side, it's the lowest. It's most clear water. So this is actually a way of estimating how clear a water is, right? So the more the clear water is, less turbid it is better for consumptive purposes. So that is where our interests lie. So we have to understand that natural processes as well as anthropogenic processes will change the turbidity and the suspended solids concentration constantly. And this change needs to be identified if we need to identify a change in the water quality itself. So another physical parameter with reference to aquatic ecosystems that is actually judged is what is known as the flow parameter. Okay, the flow or flow gauging is mainly for flowing water systems such as lakes, rivers, but it is also for canals and other systems where the water flow or volume changes will impact the other habitats or the supply of water for human consumptive purpose. Here actually the sectioning of the river, and using an impeller, the area is calculated and also the discharge as the product of area and velocity of water flow. That gives the idea of how much of water is flowing through a given area in terms of the volume also that is discharged. So this is very also important for us to understand during a precipitation event, for example, how the flow has changed. Has there been a sudden flow, or has it been, pulsed, or has it been constant over a period of time, which will also lead to other implications. So one implication is overland flooding. Another implication is loss of crops. So these are actually interrelated concerns. Where an aquatic ecosystem is concerned, flow gauging is another very, very important characteristic which determine the physical nature of water. So now actually to summarize all these parameters together with their units, we understand that for temperature, it is determined in terms of degrees Celsius, the total suspended solids in terms of parts per million, turbidity in terms of nephelometric turbidity units, odor is subjective and taste is also subjective, and flow gauging in terms of cubic meters per second. So we understand that reporting should be in this format. So for us, if we are going to look at water quality reports, we will be able to identify the increase or decrease or change in terms of the units that are indicated. So for that purpose, we are understanding these units. Now moving on to the chemical parameters point of view, a very, very important chemical parameter here is what is known as pH. So pH, we are all very familiar with pH because most of us have water purifiers in our house, and we understand that pH and TDS. TDS is total dissolved solids. We are going to talk about that. These are going to be very, very important or crucial parameters. So from that point of view, pH is determines how much of activity of hydrogen or hydrogen ions is present in water. Okay. So if the hydrogen ion activity is higher or lower, it signifies something. The presence of hydrogen ions itself, okay, H plus ions are indicating if the water is in an acidic state or is it in a basic state. So now we are actually relating the status of water to its quality. In those terms, if the pH of water that we are measuring, it is done using a meter called pH meter. So if it is neutral, it means the pH is 7. So a pH of 7 signifies that water is neutral and it is fit for consumption, or it is fit for some a set of activities that we define, such as cooking or bathing, and it will not affect us. But if it becomes acidic, okay, it goes in general, in normal 6 to 8 range is considered to be favorable. So anything lesser than 6 is called acidic. So those are not very favorable in terms of pH. Similarly, those beyond 8, 8.5 rather, they are known as alkaline, and it cannot be very favorable pH ranges for most organisms. Now, if we see here, what happens? Why is this so? When we move beyond 7 pH, that is lesser than towards the acidic range, the ecosystem characteristics also change significantly, which will affect not just the human beings, but also the aquatic organisms which are dependent upon these ecosystems. Now, first, if we see mosses, just as the slight addition of acids to water itself can cause a pH to come down to 5. And when this happens, say, mosses and harmful algae start to dominate in the water. Okay. As we go, we already discussed this earlier. We said that whatever is the acidic or the extreme nature of conditions of ecosystem, there will still be organisms which are capable of tolerating those states and still living and surviving. So from that aspect, although 5 is acidic for us, it need not be acidic for other organisms, such as the harmful algae. Okay, so their domination will definitely shift the stable states towards disturbed state. Now, this can cause what is known as massive fish kill if it goes lesser than 5, right? So up to 4 pH, fish die. And below 4, there will be release of metals into the water. We talked about actually the lowermost strata of water. If you will recall our structure of aquatic ecosystem, the lowermost level, which is known as the hypolimnion. Here, the acidity is bound to be very high, and release of metals can cause asphyxiation, and lowering of calcium will affect the egg formation for many other organisms. So this is a very, very acidic situation. Below 3, there can be no life. So that is actually the reality of pH with respect to the acidity portion. For in terms of the alkalinity portion, if we move towards 9 pH, then it actually the water causes damage to gills and eyes and skins of the fishes, which means that the fish start to die off. So you see there is a very delicate range within which life exists in an aquatic ecosystem. Beyond 9, when we reach 10, there is an ability to dispose toxic wastes. It means that there is no recirculation happening. There can be no other biology integrated chemical reactions which can help to recirculate the nutrients and dispose the toxic waste. So that is not possible. Up to 11, if we go, the ammonia toxicity sets in. This is a very, very important factor because this leads to direct disappearance of most of the aquatic life forms. Okay, so alkalinity causes the impairment of the metabolic functions of fishes and aquatic organisms, which means that the whole biota is lost. So the range after 11, the 12, the alkaline range 11 to 12 will lead to definite collapse of the aquatic ecosystem itself. So now we understand for the quality of water to be suitable for life sustenance and its use, it is a narrow range, right? 6 to 8.5 probably. So that is actually the sensitive range, and pH is very, very definitive factor which determines the quality considerations. We have already seen about water temperature, but we should also know that it is not just a measurement of how hot or cold it is, but it is also a measurement of the average thermal energy, which will cause it to remain in one particular state or phase. Okay, so this phase transition is a very unique aspect of the hydrological cycle, which will determine how much of runoff or how much of fresh water is available on land and how much is also available in the aquifers. So this is a very, very important consideration from the distribution aspect as well. And the quality aspect, it is known as the master abiotic factor. So this, in one way, it causes what is known as the vertical mixing of water layers in an aquatic ecosystem. So this vertical mixing is what actually is known as convection. Convection of these water layers will impact the circulation and the availability of nutrients across the different layers of water. Again, if we take our understanding back to the structure of a water ecosystem that we saw earlier, when there is a convection happening, we can see that the hypolimnion range will be very less. So it means that it is a well-mixed system, right, where the availability of nutrients is high from the bottom towards the from the top towards the bottom, and warmer temperatures will promote more of this circulation, which will promote more reproduction of organisms, and colder conditions will restrict also light penetration and will lead to different types of covers, which will determine the decrease the population abundances itself. So here we see that water temperature controls the metabolic rates, it controls the photosynthesis, it controls how the conduction of ions in the water happen, because ions need to move, they need the energy to move, and that energy comes from the thermal energy, right? So water's thermal energy contributes to movement of these nutrients. It also determines how the toxic compounds are being assimilated within the aquatic ecosystem. It contributes to the density of the water, and it also has a definite feedback mechanism on the pH concentrations as well. So with the movement of ions, where there is mixing, there is more a chance to establish neutral or favorable pH ranges. So now we see that water temperature is also another important critical factor of water quality. Now we are talking about ions. Specific conductance or electrical conductivity is a measure of the salinity of water. More the ions in the water, more conductive it is. So the flow of ions is very important actually to facilitate the chemical processes which allows the organisms to assimilate carbon, nitrogen, phosphorus, and also cycle it through the aquatic ecosystem itself. So this is actually, you can see on your right hand side, there is a probe which measures what is known as electrical conductivity or EC or specific conductance. So this is also related to the parameter that we call as total dissolved solids. Total dissolved solids is a sum of concentrations of all the ionic particles in the dissolved state. So this actually differentiates it from the suspended solids that we spoke about earlier, which are not a dissolved phase. Hence, they contributed to the physical quality of water. But dissolved solids contribute to its chemical composition because they are smaller than 2 microns. And this includes all the salts that we know and all the dissolved organic matter which is present in the water. So the significance of understanding the quality aspect from TDS is that it can indicate the level of pollution itself. For an unpolluted water, there should be low TDS, which we understand as also its salinity. So low TDS and low saline waters are mostly unpolluted, and the range which is ideal for drinking is 0 to 50 TDS range. Okay, so polluted waters have higher organic solutes, higher salt concentrations, and they result in higher values for TDS. Now we see two breakpoints. The breakpoints come at 50 to 100 milligrams per liter of TDS and at 200 to 400 milligrams per liter of TDS. So the first checkpoint tells us that there is a shift from consumptive phase of water towards more of ecosystem or provisioning phase of water, as in lakes, right? So if the TDS of water is beyond 50 milligrams per liter, we can say that this water is not fit for consumption, but it's fit to actually for other sustaining other life forms in water, such as the water of the lakes or water of ponds or water of lagoons. So here actually the pristine lakes with planktonic growth, they identify with a TDS range of 50 to 100 milligrams per liter. If we move slightly above, where the rock formations or other formations contribute to more salts coming in, the ranges will be 100 to 200. But the checkpoint, if we say 200 to 400, again changes the dimension of water use. Here the TDS is very high, 200 to 400. It is not fit for consumption, and it is not fit for classification as a freshwater ecosystem. Now the classification gets turned into brackish water. So this shift is also very, very important, but it is still under what is known as a tolerable level. And this TDS can be contributed in different ways, like rock formations from mineral springs in the area. And this can actually also support life forms which are able to tolerate the brackish water. So here, the shift from freshwater to brackish water ecosystems is what is determining the ecotonal quality of an aquatic ecosystem. Now, the aquatic ecosystem is no more a classified freshwater ecosystem, but is an ecotone which supports both freshwater forms and salt, brackish water forms of life, of biota, of flora, fauna, which can tolerate such ranges of TDS. And above 500 mg per liter of TDS, it is called a very highly polluted lake or a hypersaline system, which will not support so much biodiversity as the brackish water or the freshwater systems. So this is actually not suitable for any other purpose as well. There is also, from the managerial point of view, a TDS of about 200 to 400 is typically a manageable range. Okay, in some places the TDS, in one of the classes when I showed this slide, somebody told me the TDS in our area is close to 700. Can we still use it? See, this is actually a challenge, because above 400, it is not fit for consumption, definitely, and it is not fit for treatment also most of the times. Okay, so if we have to have treatment of water which can bring down its TDS and it can be reused, our limit is 400 to 500. So beyond 500, it's absolutely not worth it, because the amount of energy and materials and efforts which are invested in actually reclaiming the water to a TDS which is of comfort or convenient level to us is much higher. So now we understand that the characteristic of water in terms of TDS also becomes a very, very critical factor. Moving on, another critical factor in terms of water quality is what is known as dissolved oxygen. So the dissolved oxygen is the measure of oxygen that is present in dissolved form in the water. Now we can see that there are biological processes which will alter the way in which the DO is actually present in an ambient situation as well as in an altered situation. So if we see from an oxygen supplied through a river water, okay, the oxygen diffuses from the atmosphere into the water, and where plants and algae, they produce oxygen when they photosynthesize, which means that there is saturation of DO in this scenario. But in the respiration scenario, we can see that there is consumption of oxygen that is happening, where the respiring bacteria use up more of oxygen. When will the bacteria and algae which respire use up more of oxygen? Because when they want more of the nutrients to be assimilated, that means more of nutrients is present, more of oxygen is taken. So DO levels will determine how nutrients will be used and recycled. So if the DO is very less, for example, we can assume that under low DO condition, the nutrient richness, okay, will also be low typically. But if actually the low dissolved oxygen is present, but a high nutrient level is present, it is an indicator of a change in the state from a stable to an alternate state or a disturbed state, probably. We can call it in terms of eutrophication, because with the increase in nutrients, as I said, more of oxygen is being used up. Okay, so now we have to recall our oligotrophic, mesotrophic and eutrophic conditions that we discussed earlier, and the hypereutrophic condition. Oligotrophic, nutrient concentration is low, DO is also low. In the meso, moderate amount and low. Moderate amount of DO and moderate amount of nutrients are present. Whereas in the other phase, if we see the eutrophic phase, there is low DO but high organic and nutrient concentration. Here, the dissolution of other gases will also be impacted. So there is actually a feedback condition which is set in because of the presence of or the status of DO which is dissolved in the water through saturation. So this is not just present in the lake or the river or the lagoons that we discussed, but also throughout the sea, right, the ocean. So here there can result in zones where there is no oxygen at some point, which are known as anoxic zones, as I already mentioned, at higher depths. And also there can be zones which are termed as oxygen minimum zones, where the oxygen is very, very less. So the sustenance of life, again, you see, is very sensitive to the concentration of DO, which is present in different layers at depths differently within even different ecosystems. So if we move on, another one very important aspect in recent times, which has affected the water quality in general, but is being monitored majorly, is the presence of microplastics. And I would like to discuss this along with the nutrient recycling and the DO that we are seeing. So in this slide, you can see that the microplastics, their concentrations increase when even under nutrient limited conditions. Okay, so actually their consumption of oxygen goes down, nutrient is limited, but the increase in ingestion of microplastics will increase within zooplankton and the phytoplankton or the biotic components which are present in aquatic ecosystem. This is actually an observation which tells us that the ingestion of zooplankton and phytoplankton is very, very, impactful on the overall quality over the rest of the period of time, because if more of these microplastics are ingested, the population dynamics is going to be skewed over a period of time. It is going to fall first drastically, but it is going to be transferred or present as through a mass balance. It is conserved in the water ecosystem itself, and it's not moved out. So there is no way that we can get rid of these microplastics over a period of time. So we also have to concentrate on the integration of physical factors such as plastics, debris, litter, along with their integration with how they are actually ingested or taken into the biotic cycles. Right here, we can see that this particular study was done in the ocean with respect to what is the water column dissolved oxygen status and the consumption statuses when more and more of these microplastics are present. But this is very much applicable to even shallower depths. More of research is undertaken in these lines these days. But initially we see that nutrient limitation does not matter to microplastic ingestion, but actually it has a very big impact on how oxygen is consumed, and that will actually indirectly impact how the nutrients are recycled, as we saw earlier. So this is a very intricately related situation where the cumulative impact on water quality is determined by different parameters which come together to determine what is its status. And having had that status, we have to also refer to the concentrations of dissolved nutrients. So you see there are two pictures here, and both the pictures show natural aquatic ecosystems where there is massive fish kill. You can see the dead fish are floating on the water, right? So when there is excessive nutrients, it may not be always good for an aquatic ecosystem. Higher nutrients, as we saw from the stoichiometry yesterday, higher nutrients does not always mean that they are utilized in the same way. So there can be limiting nutrients and there can be non-limiting nutrients. The presence of excessive nutrients will cause what is known as algal bloom, and that will actually have a deteriorating effect on the dissolved oxygen concentration, because more and more oxygen is stripped to recycle what are the nutrients, excess nutrients that are available. So excessive levels can result from human impacted processes such as agricultural runoff and artificial enrichment of water. It can create tough conditions for survival of other biotic communities such as insects, aquatic insects and fishes. So anoxia or lack of oxygen can also be result of this excessive presence of nutrients in aquatic ecosystems, especially lakes, where there are no big exchanges happening with adjacent system. If it is an enclosed system or isolated system, the impacts are greater. So this actually limits the productivity and the ecosystem services, provisioning services of aquatic ecosystem. So these are actually measured. Just to have an idea of how they are measured, this is actually a photograph of a spectrophotometer, which is used in a lab to measure this as a function of the intensity of absorbance. So here, actually, the scattering capacity of light is actually standardized with reagents which are mixed with the sample, and the absorbances here, you can see the absorbance is shown as 0.023, which is pretty low. That means the water, the amount of nutrients which are present in this water may be lesser. It is just indicative, but it may be lesser, which means that it can be an oligotrophic water where the concentration of nutrients itself is less. So this is some way in which we try to determine the status of water through chemical analysis. And to summarize the chemistry or the chemical water quality parameters here, pH is unitless measure, whereas specific conductance is reported in terms of microsiemens per centimeter. The concentrations of dissolved nitrates and phosphates in terms of milligrams per liter. Dissolved oxygen is measured as parts per million, and most other chemical constituents are measured as their mass per volume of water. Now moving on to the biological quality. So biological parameters are also actually measured in terms of the bacterial population, basically at a very basic level. Okay, so we have to understand that bacterial activity will increase with increase in amount of substrates, and these substrates will come from mostly the presence of domestic sewage, right, where they grow and they survive. So here, what the two parameters called fecal coliform and general coliform, these are estimated by taking a sample of water, and they are actually put in petri dishes. If we can recall our labs, they are actually inoculated into the medium which is there in the petri dishes and incubated, and then the number of colonies are counted. More the number of fecal coliforms will indicate more of domestic sewage entry into the lake, which is spoiling the lake water quality. So this is a microbiological indicator. That I gave that as one of the example. Other examples are E. coli, coliform bacteria. From a human health perspective, these are very important, especially when we are trying to achieve the goals of sanitation and hygiene. The bacterial indicators become very, very significant. Bioindicators, apart from bacteria, can be large insects and animals also. How do they indicate? For example, the movement of locations of fishes can indicate that there are certain conditions which are not very favorable for them to survive within a given aquatic ecosystem. But this actually can be in terms of different ways of assessment. It can be a quality based on its chemical environment or on some physical factors as well. For example, the presence of a temperature boundary or a thermocline layer, which is not suitable for their development or growth. So the fish move away. Okay, so fish move also away from hypoxic layers where very low levels of dissolved oxygen are present for them to respire. So that becomes what is known as the oxygen boundary. Another boundary is called the nutrient boundary, or where there is excessive nutrient, fish will not survive, as we have already seen. So if there is, for example, these three boundaries are indicated by the movement of fishes, we can say that the quality of water at this point is not very well established for actually sustenance of life. Another indication is by a movement of organisms into the aquatic ecosystems where they were not previously present. So these can be either part of the migratory routes, or it can also be part of invasion. Okay, invasive species moving into new locations. So these are all indicators, but they have to be actually put together in terms of large monitoring of data sets in order for us to sum up where the quality of water has changed and where it has been disturbed and where it has found an alternate stable state. So now we understand that parameters such as pH, dissolved oxygen, conductance, alkalinity, nitrate, phosphate, they will help us to categorize the quality of water for normal or treated use. Okay, so this is very important indicator of the ambient status. But actually, some other specialized parameters such as presence of heavy metals, presence of pesticides, presence of industrial waste, pharmaceuticals, and surfactants. These are very sensitive parameters present in very small quantities. After primary treatment, or does it have to go through secondary, tertiary, or advanced filtration treatments? So with this, we also come to the concept of best use criteria. Okay, so not all classes of water can be used for all purposes. Here you can see CPCB has actually categorized the water into classes A, B, C, D, E based on their total coliform concentrations, pH, dissolved oxygen, and another important parameter which is known as biochemical oxygen demand, or BOD, which along with chemical oxygen demand will help us to estimate the extent of domestic or sewage pollution as well as industrial pollution. So BOD or biochemical oxygen demand indicates sewage pollution, and chemical oxygen demand is an indicator of the extent of industrial pollution in water. So given these criteria, sets of criteria that are given here, you can use water accordingly, according to the class that it fits in. So this is a very important parameter for us to understand. Apart from just the permissible levels, there are what are known as tolerance levels. So tolerance levels are the maximum extents up to which the particular water can be used for that particular service, okay, that it has been designated for. So now we see that water temperature, pH, TDS, nitrate, and phosphate by themselves can actually give us a clear view of what is the quality of water and what are its tolerance limit, up to which it can be used without any sort of risks. Now we see that there is a three-part problem from our discussion till now. It is not just about the status or availability of water, and it is not just about the use quality of water, and it is not just about the sustainability, but it is for us to understand that these are linked to what are known as the changing trends in the demand for fresh water, and those the changing demand and how the rate of pollution is happening of these resources, and how the distribution or uneven access is changing the way in which water is being categorized and used or reused between populations. Now we can appreciate that the extensive nature of quality assurance that goes into determining the water types is very, very essential part of our framework for determining the sustainability of aquatic ecosystems. So now we move on to discussing how the competitive uses, and there are issues regarding this in terms of the consumptive use as well as the competitive use across different sectors. So the core principle in usage of water ecosystems is that first, they should be able to provide safe and affordable drinking water. They should also be, reservoirs there where the wastewater is treated and it's safely reused in many multiple forms. By improving the water use efficiency, we are able to conserve and preserve our water assets, and this leads to what is known as integrated water resources management. So it is not just about the consumptive use, but it is also about how we reuse and how we actually improve industrial use. So these three factors are very, very important concepts which help us to determine how well we bring in the concept of integrated management approaches. Not only that, water is also an element which is water is also a component which is actually very increasingly being shared. So when it is being shared, there is supposed to be some sort of transboundary cooperation in using these resources, which will also determine its distribution and its access. So here, apart from the aspects of integrated water resource management across the three sectors, it is also an important consideration from the sustainability point of view for us to understand that the transboundary aspects of water should be addressed for the distribution, and the status to be favorable for our use, okay, in different regions of the world where there is unequal distribution or unequal access. Finally, for long-term sustainability, we should also consider how they are recreationally used, because most water bodies can be recreationally used and they contribute to some sort of economy, but they actually can cause more degradation of these activities of recreation or ecotourism that we call, can cause higher levels of pollution to the ecosystem, which means that the protection and restoration of these ecosystems will take precedence in some point of time, which will lower the economic viability. So among our three pillars, the social, economic, and environmental pillars, the sustainability concept should actually foresee these scenarios and usher in what we know as conjunctive water use scenarios, which we are going to discuss. So we understand that water is not confined to that SDG 6 goal itself across the SDGs, but it also concerns the SDG 14 goal, which states life below water, and with the theme to conserve and sustainably use the oceans and the seas. So here, actually, we understand that the water ecosystems, they are connected and the continuum exists even in the sustainability perspective, right? So it is not just a physical continuum that we thought of and we have seen, or not just the chemical continuum that we have just seen in terms of its quality, but also in terms of sustainability. There is actually the continuum across these three pillars, the socio-economic and the environmental pillars. Now, to understand its relevance to sustainability, we have to discuss this in terms of the capacity, flow, and benefit dimensions. So now if we say capacity, we are determining what is the available renewable water or the groundwater, and the surface which is occupied by ecosystems which can supply this water. So that is actually the capacity estimation. The flow estimation dimension should consider what is the abstraction per sector that we have discussed earlier, and as well as from the chemical point of view, how chemistry contributes to flow is through how much of nitrogen is retained through a mass balance, how it is retained or it is removed, because that is going to determine what is the quality that is fit for consumption or distribution. And hence we can determine what is the benefit of across the sectors. Number one is through the cost of water per sector, industry, irrigation, or domestic, and what is the cost benefit avoided when water treatment is avoided. Okay, so if the benefit is avoided because water treatment costs are higher, it means the benefit is low, right? There is no benefit. So if the costs are avoided for water treatment, then the benefits are high. It means that there are several types of indicators which can help us to understand sustainability in terms of capacity, flow, or benefit. That is actually number one is what is known as water exploitation index, which actually is the sum of the water consumption as a fraction of available water given the capacity, its flow, and the benefit calculations. Second is efficiency of nitrogen retention. So what is the nitrogen which is retained as a fraction of the total input? So what this translates to is that the indicators will actually indicate the provisioning services and the regulatory services of aquatic ecosystems. So regulatory services in terms of water purification. Okay, so that is one very important indicator of the services aspect itself. So now we see that capacity will indicate potential to deliver the service, whereas flow will help us to determine the flow of action and implementation of the policies which will help us to sustainably manage these services. And finally, the benefits will reflect upon the actual human health, well-being, and the value system and the exchanges, knowledge exchanges. So now we understand that the aquatic ecosystems are structurally more consistent than dynamic, although physically they can be more dynamic in nature. They are actually a well self-regulating, sustaining systems. So here the dynamicity due to non-linear reactions are under control if the sustainability is not compromised. And for sustainability not to be compromised, the functional characteristics with respect to the factors that we have determined has to be preserved. So now we know that the complex interactions, just as we discussed, between the geology, climate, land management, and modification of land use, these are the very, very important factors which will determine what is the quantity of water that is available, as well as its quality. While this data goes into decision making with the ability to predict the effects of the land use and change in climate scenarios, which will contribute to how much of distribution or access of water is available across different parts of the globe. So this 1, 2, and 3 tell us that availability, distribution, quality, consumption, competitive use, and sustainability will actually determine how well the ecosystem services aspect is preserved. So now provisioning aspects, not just for drinking or consumption, but also as in the part of food provisioning, because they sustain fisheries. That is one very important factor. Another important factor is by for flood protection as one of the service, or erosion prevention as one of the service, as also carbon sequestration. We discussed these aspects. All this form part of what are known as the integrated assessment framework of the drivers, the pressures, and the statuses, which will help us to understand what are the new age water centric issues, because there are three major issues. One is we have to model exactly what is the availability versus the use. This is very big optimization which is required. Second is to plan the reuse for different end scenarios. So the end use scenarios will vary. We know that across sectors it is going to vary. It may not be always consumptive, as we have just discussed. It can also be for manufacturing. It can be as coolant water. So the end use varies. It can be for irrigation. So the reuse of water has to be planned differently in modern times. And third is whether there is a consideration to create new water assets or new water infrastructure. So in this way, we come across the idea of conjunctive water management, which will help us to achieve these three categories that we just saw. So UNESCO defines conjunctive water management as an approach to water resources management in which surface water, groundwater, and other components of the water cycle are considered as one single resource, and they are managed in closest possible coordination, so that there is maximum overall benefit which is derived from the water at the short and at the long terms. So this is a very wonderful definition which helps us to understand that the hydraulic connectivity between different components operating in the natural water cycle should not be lost. If these direct linkages are not lost, then the human value chain based on the water supply and demand chain can be established. Okay, so there are several indirect linkages which will systematically lead to a better management approach over different water cycles. So this particular central idea is known as conjunctive water use or conjunctive water management. It is an integral part of what is known as the integrated water resources management. So two important aspects are very important in this. First is to address the correct technological requirements to achieve conjunctive water use. And second is to address the equity issues and predicting the production issues which are associated with, again, the conjunctive water use. So now we concentrate both on the groundwater and surface water as one component and not as separate components. From a mass balance approach, we can determine them as separate components, but as we have seen through our lecture today, we know that they are interlinked. When they are interlinked, increasing the water availability on surface should also be synchronous with how much of groundwater availability is increased. So this is where implementation of technologies such as meteorological advisories, which will say that so much of rain is going to be received, will help us to create water assets which can store this rainwater for a long-term or a short-term use. So now we know that we should also the activity of bore wells which are present per square meter, policy on that will help us to optimize how much of groundwater drawal is happening, and also it will help to prevent how much of salt water is intruding into the freshwater aquifers. So a planning with technology and a planning using water assets together can help cities and rural townships be an integrated model for managing the demand versus distribution, especially during the peak periods and especially in places where the population is high, as in the case of India. This is one example from Bangalore, which is actually given by IASC. IASC study Envis technical report tells us that the rain, if you see, notice that there are three components which are circled. Okay, the rainwater yield, the sewage, and the reuse or the disinfection pools. So these pools are very critical because they can help actually to increase the storage capacity, and they can help to increase the sustained release as per the demand. Okay, and these are a very improvement, the improvement in the treatment technologies. On one side, we thought the asset creation is important. The second approach is increasing the treatment technology, which can increase the freshwater recovery, which makes actually the water availability higher. So in this way, it's a very good model of conjunctive water management approach, wherein the water scarcity of Bangalore city can be managed. So this model tells us that it's not just rejuvenating the ecosystem, but retaining the water, recycling and reusing the water can help us to actually improve the way in which water is managed. This slide shows different types of other approaches which can help in conjunctive water use. I'm not going to go into detail, but we have to understand again that in the perspective of using technology, along with actually, treatment technology, along with increasing the assets, those together, assets versus technology, can change the landscape also in different ways. So without changing the landscape, but also analyzing what other aspects can be, changed from the stable state of, for example, of an adjacent ecosystem as land, we should actually plan IWRM. So the concept of associating land with water becomes very, very critical for us. So over also not from the population point of view, but also from other additional storages point of view, the food security point of view, management of conjunctive water use approaches or options. Several models are shown here. These are all very, very important ways to manage the conjunctive water management scenario for different regions. Now I'm taking your attention to another very, very important discussion on how water and energy are related. If you recall our first slide where we actually, saw the different dimensions of water as an ecological unit, as an environmental link, we came to the point when we discussed the link of water with energy. So now if we see that high irrigation demand and pollution of water, water systems through runoffs from agriculture will create less fresh water for drinking or industrial use. This is one outcome that we actually can predict. Another outcome that we can predict is if there's a contaminated municipal or municipal water supply or an industrial wastewater which pollutes the rivers and the lakes, it will threaten the ecosystem existence over a long period of time. This can actually result in lower water availability. Okay, so another way in which this can happen is that if water is left in a river to protect the fisheries, and there will be less to divert to grow the crops. But for all these issues, managing these issues, may it be the pollution aspect, may it be the irrigation aspect, or may it be the fisheries aspect, we need what is known as energy. That is why it is said that 90% of global power generation in terms of even thermal, if for example, if we take the thermal power plants, mostly it is water intensive operation. And water is also drawn up to 90% for, especially for power generation alone. So here the challenge is for us to overcome the 50% consumption increase in consumption of energy by 2035 by not compromising on water, where it is also predicted by 2035 the consumption of water will also increase by 85%. So now you see the balance or our perception shifts from just the challenge of maintaining good quality of water to also using water to produce energy and electricity in the coming years. Now, if we look at different ways in which these are being handled by technology these days, there is several, we have to understand that not all technologies can be useful for us to address water shortages versus the power generation issues. For one example that we can think of is the solar power plant, which is shown here in Abu Dhabi. Okay, so solar power here is because of the presence of high heat and thermal energy in this region. Solar mirrors in a Shams 1 solar concentrating power plant, it was set up to harness the solar energy to produce electricity. How this can impact water shortage is shown on your right hand side. See, there is dust accumulation on all these solar mirrors. As you can see, there is a robotic arm which is cleaning that by spraying water. The water needed is about close to 7,000 to 20,000 liters per megawatt of energy generated per week in this solar concentrating plant, which means that even an increase in the dust of 1 gram per meter cube can decrease the output. So it has to be, so much of water has to be invested to have the generation constant and not decrease the output. Also, we have to ensure that monsoonal impacts can have change the energy production of the solar concentrating mirrors, which means that there is an element of unpredictability in how much of energy output can be achieved by investing still 7,000 to 20,000 liters per week of water. And see, we are going to we have to understand that the decrease in the performance is guaranteed over time. But what about the water demand? How are we going to manage that? So this is a new age centric issue which is very relevant for us to address. In India itself, if you see 2012, actually there was the largest blackout that plunged about 600 million, approximately 670 million people into darkness because farmers used excessive electricity to pump the water to compensate for the poor monsoon season output. Okay, so here is monsoonal unpredictability combined with actually the need for energy versus water can actually cause huge water stress conditions. And these water stress scenarios especially are relevant in states such as Gujarat and Rajasthan, which are where the more of installed solar projects are coming up. But the capacity also has to be balanced with the water scarcity or water stress issues that India is facing. So one way India is managing is by promoting water on a small and micro hydro projects. These are very, very useful conjunctive water management scenarios which help us to competitively use water for different purposes. I'm not going to go into detail, but just to show there are different types of small hydroelectric power projects which are very, very suitable to have a self-sustained system in place or self-sustained societies, right? So projects such as mini, micro and pico projects, and also the projects that you see here, especially which are installed. This is from Italy and they are not from India. The one on your right hand side is from India, where a pico level hydro project which generates power under 5 kilowatt is established. So both of these can give differential outputs, but it can also help to sustain the way in which energy and water are balanced. So here another very from a farm level approach to a very small residential level approach, it is possible for us to harness the energy, hydro energy, for generating power, which is actually a very good output or a good way to manage the energy water balance again. So now this slide, with this slide we come to all the discussions put together which result in what is known as the issues in equitable and just distribution of water resources. This is actually a page that I came across from my son's 5th standard environmental sciences textbook of NCERT, which was very, very beautifully, it showed the way in which the inequalities in existence with respect to water resources itself. For example, there are scenarios where one of the children tells that we get water in tankers, but we have to stand in a big queue and there are always fights. So water is available, water has been distributed, there are no quality issues, but there are still access issues. Now, if we see on the other part, on the right hand side, the child says we get water through the pipes, but it is only about for half an hour that we receive. Okay, and we have to use the same tank the whole day. sometimes it is polluted and it is dirty, which means that the issue is of quality and the issue is of time as well. So the access is limited by time and the quality. There are other issues like usage of water through, the people have to put more effort using hand pump to get water, but it is still of not good quality. It can be salty, and so they have to go and buy again water, extra water for drinking, which they have to spend more for getting better quality. So the issue here again is not of access, but it is more of the availability of good quality of water at a higher cost. Now, if we see, seasonality plays a big role, because one child says we get water from the canal itself, which is not treated, which can have agricultural runoff, and it can impact the public hygiene and human health conditions very, very badly. Another child says we get water in a pump pipeline directly from the the water board's pipeline. We just pump it. But the question here is not access, it is not quality, and it is not distribution, but it is more of ethical nature, because giving bribe only will result in the access to this use of water. So where do we stand in terms of loss of service or inequality, or in terms of using more energy to get more water? We saw that there can be scenarios of conjunctive water management which can be adopted to ensure that there is equitable distribution of water, there is equitable access, and there is equitable reuse of water scenarios. But where do we stand in terms of intra and intergenerational equity? And where do we stand in terms of water justice? It is a very delicate situation, if we will say, because the competitive uses of water will have, on one hand, the importance may be given to a societal cause, or at some instance it can be given to an individual cause. So there is always going to be a mismatch. And I think that this very page, which comes in a class 5 textbook, is very, very relevant, because it tells the children the core of sustainability, which is going to, they have to imbibe in their lives through generations. It's a very positive development, and it's very, very important development, because all children want to be like that child on your left hand side who says we have absolutely no issues, we get water from our taps all day long. I would beg to differ from this child, because she's saying no issues, because it's a very nicely made picture. You can see the tap is still open behind, and there is irrational use of water, right? The water tap is open and it's not closed, which means that there is excessive loss or wastage of water happening, which is the core issue. I want to draw your attention to that very picture, and we have to actually surmount it in terms of all the approaches of sustainability that we have taken forth and to understand today, through the different aspects of water, through its status, distribution, quality, as well as its competitive use. So with that, I stop today, and I'll be happy to take your questions. I apologize for the two very big disturbances in the network, but I hope that we have covered all grounds today, and be happy to have more discussion. Thank you.
Thank you, ma'am. The last slide was really nice.
Thank you. I too like the slide so much, because it's very, I would say, insightful.